you guys can have time to finish to do your projects. Okay. Image representation and description. Okay. This is usually the task that we do after the segmentation. Okay. Once you have segmented an object, okay, now you want to represent an object, okay, by a certain description, okay, and that's how we call the image representation and description. Here are some of the representations, okay, and some descriptors. Okay, there are two kinds of descriptor: the boundary descriptor and regional descriptors. Okay, but this is just some of the basic ones. Okay, you probably there nowadays there are more and more advanced. You know, the way to describe objects. Usually, do it by statistics. Okay. Anyway, representing an object. Okay. After segmenting an image into regions, okay, the objects and the background, we need to represent each region by a more suitable way for further computations. Okay, for further computer processing. Okay. We can represent the regions in terms of the boundary. Okay. Sometimes we call it the external characteristics. The boundary of the object can be described focusing on the shape of the objects. However, another way to represent could be the region, okay, or the internal characteristics. Okay. The regional property, for example, the colors, the textures, okay, these are the internal or the region characteristic. Most of the time we need both. Okay, we need both regional and boundary characteristic. Boundary is just concerned with the shape. Okay, like the length of the boundaries. Okay, or the how many turns are in the boundary and so on. Okay, the region are within the objects. Okay, usually it provides some distinctive details. Okay. Description is to describe the region based on each representation. For example, boundary representation, the description could be the length of the boundary, could be the orientation of the straight line that joined the extreme point, could be the number of concavities, okay, within the boundary. For the region representations, the description could be the area, the colors or the intensities, the texture or the smoothness of the objects, okay, or the number of holes in the regions. Okay. So after segmentation, okay, you can get raw data. You have objects. Now you want to represent the objects by a more concise data. Okay. These raw data sometimes can be used directly or to obtain the descriptor. However, most of the time it's not, okay, because there might be too much redundance in the information. Okay, that's why we need something more compact, okay, simpler to manipulate. Okay, we want to compact these raw data into the representation that is more useful and easier to compute. So basically, the segmentation, after the segmentation, we need representations, the data compactor, and you got the descriptor. And this descriptor, usually we call it the features of the objects. Okay, different object may be characterized by a set of features. Okay. Usually, a lot less than the raw data itself. Okay. let's do some of the things that we're going to be doing today, which is the chain code, the polygonal approximations, and some boundary segments. Okay. Shall start with the. Before we start, there will be some features that we can select as the descriptor that should be insensitive of. Okay. When the feature is insensitive to a certain variations, okay, sometimes we want that. Okay, for example, this heart shape, okay, if it's getting bigger, should there be a different descriptor? Suppose we're looking for the face of the human, right? It could be human face, but if you zoom in, you get a bigger face, a smaller face, or if you zoom out, you get a smaller face. But in that case, if you use the pixels, the number of pixels, it might not be good because it varies depending on the objects, right? The size of the object. So sometimes we don't want the descriptor to be sensitive to size. That means even though you got a different size of the object, it should be represented by the same set of descriptors. Okay? We call this set of descriptor invariant to size. Okay? Or invariance to translation. This is what we usually want. Okay? It doesn't matter where in the image it happened. Okay? It should be described by the same descriptor. Okay? So it should be invariance to translation. It should be invariant to rotation. Even though the object is rotated, the descriptor should stay the same. Okay? To be insensitive to rotation. These are some of the features that we prefer. Okay, most of the time we prefer these features. The features that is invariant to size, invariant to translation, invariance to rotation. Okay, let's take a look. The chain code is one way to represent the boundary of the object. Okay, by connecting the sequence of straight line segments that specify length and direction based on 4 or 8 connectivities. Suppose we have the 4 connected. Remember last time we learned the 4 connected, right? Okay. So we've got 4 connected. Then if it's connected like this to the right, it's going to be represented by a 0. If it's connected top to the top, it's a 1. If it's connected to the left, is a 2. If it's connected to the third to the south, it's a 3, and so on. So this is based on the 4 directional. This is called the 4 directional chain code. Sometimes we can do the 8 connectivities. Okay, if the pixel is connected like this, to the right is 0. To diagonally this way is a 1, 2, 3, 4, 5, 6, 7. Okay, this is called the 8 directional chain code. For example, suppose we start with a pixel on the boundary. Okay, suppose most of the time we start from the top left corner of the object. So we start with this object. Then we will read along the boundary. How do you read along the boundary? For example, here you go to the left. So it's go to the right, okay, go to the right, so it has 0. And then go to the right again, is another 0. So we're going to read 0, 0, 0, 0, 0, 0, and then goes down this way, diagonally. So according to this chain code is 7, okay. So it does 0, 0, 0, 0, so this is what we read. 0, 0, 0, 0, 0, 7, and it goes down, directly down is a 6. So you got 6, 6, 6 here, 6, 6, 6, and then 7 again, and then 666, and then 00, and then 66666, and so on. So you read along the boundary, you get these chain code. Okay? So instead of keeping this object, we no longer need to keep this object. You translate it into a chain code like this. Okay? You can translate it into a chain code like this. So if I give you a chain code, can you draw the object? Of course you can. But which one is easier to represent? The chain code, right? It's more compact. Okay, it's more compact that way. Alright. However, this chain code, they say there's some problem with the chain code. The chain code resulting tend to be quite long. First of all, the chain code of an object usually long, and any small disturbances along the boundary due to noise or imperfect segmentation may cause the chain code to be different, even though it should be the same. Okay, or so the chain code may not be related to the shape of the boundary. But actually, this is the details. Right? So the solution is to resample the boundary by selecting the larger grid space. Okay. So for example here, okay, this chain code, which is too much, too many points, too many dots. Okay. You might want to represent it by a larger grid, okay? To represent maybe here, like this part on the right hand side here, you can see there are many turns, okay? Which may not be necessary, okay? So we draw like this instead, okay? It can be 4 connected or 8 connected, okay? If it's A connected, then this long chain code reduced to just 0, 7, 6, 6, 6, 5, 5, 5, 5, 5, 3, 3, 2, 1, 2, 1, 2. Okay, a shorter chain code. Okay. Or if it's 4 connected, it may be represented by 0, 0, 3, 3, 3, 3, 3, 2, 3, 3. So the 4 connected chain codes is only 0, 1, 2, and 3. Okay? So this chain code is shorter, okay, and it can represent the overall shape of the object. Okay. Just need to be careful that different grid may generate different chain code, though. Another thing we might want to do is we call it the starting point normalization. Usually the starting point in the Freeman chain code, the chain code that we just talked about, okay, usually it's arbitrary. You can start from anywhere, okay. However, to normalize the generated chain code so that chain code with different starting point may have the same chain code. This is similar to, having the rotation part, okay? Chain code, if it's rotated, okay, it should end up with the same chain code, okay? We will treat the chain code as a circular sequence, okay, of the indirection numbers, okay? And then we choose just the sequence that give us the smallest or the max integer of minimum magnitude. What does it mean? This is what it means. Suppose we got a chain code like this: 2, 0, 3, 3, 1, 0, 1, 1. Okay. You can treat it as a circular sequence. So instead of just starting from 2 and end at 1, you think of it as a circle like this. So it's 2, 0, 3, 3, 1, 0, 1. And then, so it could be any of the chain code. Okay, it could be any of the chain code, but we'll choose the one with the smallest magnitude, the minimum magnitude. Okay, so in this case, you choose, well, if it's smallest magnitude, usually it starts with 1, right? So it could be 1 0 0 1 no sorry, start with 0 0 1 3 3 1 0 1 1 2, which is this one. Or it could be 0 1 1 2 0 3 3 1, which is this one. Which one of these has the smaller magnitude? The second one. Yeah, the second one is smallest magnitude. So in this case, we say this shape can be represented by the smallest one. So if I offer you this shape, okay, everyone else would get the same chain code. Okay, if we agree on this rule. Okay. Next is rotation. Okay. Rotation normalization. An object with the same shape but different rotation may end up with different Freeman chain code. Okay. For example, here this object here. Okay. The number of directions. The first, this one, if you treat it like this, the chain code would be. Suppose we start with this, right? So it goes 0 0 3 3 0 0 3 3, and then 2 2 2 2 2 1 1 1 1 1. So we end up with this chain code. Okay. However, this one is the same chain, but it's rotated. What happened to this chain code? The chain code is this one. 0 0 0 0 0, and then 3 3, and then 2 2, and then 3 3 2 2 1 1 1 1. You can see that these chain code and these chain code are two different chain code. Okay, that means these two represent two different objects. Of course, they are two different objects, but if we take a look at this object, it's the same object, right? But it's rotated. Suppose we want another descriptor that is invariance to rotation. What should we do? To be invariance to rotation, we use the first difference. It's more like taking the derivative. Okay. The first difference. What does it mean by the first difference here? The first difference means you take the difference between this and this. Okay. 0 0. What's the difference? 0. Okay. 0 0 is 0. 0 minus 3. 3 minus 0. Okay. This one you got 3 minus 0 is 3. 3 minus 3 is 0. Okay. 0 minus 3. Actually, 0 minus 3 is negative 1. Right? But our chain code suppose we have no negative 1, so you modulo by 3. Negative 1 modulo 3 is 0. 0 minus 3 modulo 3 is 1. So it's like it goes from 0. Here, this is like you go from 0 to 0, which is 0, and then from 0 to 3. So you turn this way, 1, 2, 3 here. And then 3 to 3 is 0, and then 3 to 0 is 1 here. You go from here to here. Okay, this direction. 3 to 4, 0 is 1. And then 0 to 0 is 0. And then 0 to 3 is 3. Okay, you turn this way, okay? 3 to 3 is 0, and then 3 to 2. How much is 3 to 2? Right? 3 to 3 is 0. 3 to 2 is 3. 1, 2, 3. You see that? Okay. Or you can say 3 minus 2 minus 3 is negative 1. Modulo 3 is 1. Hold on. Negative 1 modulo 3 is 3. Right? So this is what we read. Okay, and 2 to 2 and 2 to 1. 2 to 1 is 3. Okay. 2 to 1. Change from direction 2 to direction 1 is 3. Okay. And the last one, however, okay, you need 1 goes to 0. From 1 go to 0 is 3. Okay, so you need a 3 here. Okay. You got to circulate, okay, from the end. So according to this shape, we did do the same logic, okay? 0 to 0, 0, 0 to 3 is 3, okay, and so on. And then you choose the smallest values, okay? Yeah, this one doesn't seem to be the same, but if you choose the smallest values, okay, the starting point normalization, you end up with the same chain code. Okay, you end up with the same chain code. So this chain code is invariance to rotation. Okay, this chain code is invariant to rotation. We call this chain code the shape number. Okay, the shape number, because it represents the shape but not the orientation of the shape. Okay.
starting point เราเมื่อไหร่ที่ท่านมาทำยังไงนะครับ
Here, not starting point normalization, just like in the previous one. Here, see, you think of it as circle, and then you choose the smallest. So according to this, the starting point. So you treat these chain codes as the circle, right? You read 0, 3, 0, 1, 0, 3, 0, 2, and then you pick the smallest value. The smallest value is the one that leading zeros, right? A lot of leading zero. So in this case, it's the 0, 0, 0, 3, and then 0, 0, 3 here. Okay, this is the starting point. Starting point here, and for here, this is which one? This one is the starting point. Right? 0, 0, 3, 0, 0, 3. Okay, this is the starting point. Okay, you start here for this chain code. You start here for this chain code. Okay, and you end up with the same chain code. Now this chain code, this is not called Freeman chain. The original one is the Freeman chain code. This is called the shape number. Okay, because it's, even though the same shape is rotated, you get the same shape number. Okay. Any question at this point? Yes.
อันนี้ใช้ได้เฉพาะแค่ที่เรามีแกนแค่เท่ากัน
แกนเท่ากันหมายถึง
มันมีแค่0 ถึง 3หรือว่า0 ถึง 8
ใช่0 ถึง 3 หรือ 0 ถึง 7 This is the 4 directional chain code. It works for also the 8 directional chain code as well. Okay. Next is polygon approximation. How do you approximate a polygon? Okay. A boundary can be approximated by arbitrary accuracy by a polygon. Okay. So if you got a very long boundary, okay, you might want to set about the essence of the boundary shape with fewer possible polygons. There are, usually it's not trivial and it can be time consuming. Okay. For example, there are 3 techniques. Okay, the minimum perimeter polygon, the merging techniques, and the splitting technique. The minimum perimeter polygon, it means if you got a shape like this, you put it into a grid of distance d. Okay, the distance d. And then you think of this boundary as an elastic. Okay, เป็นยางยืดหยุ่นได้นะครับ and this elastic boundary will shrink itself, okay, onto the grid. Okay, onto the grid. So you think of it this distance, okay, will shrink to this boundary. This distance will shrink to this boundary. So it ends up with polygon instead of, curvy chain code. Okay, so with this polygon, then you can represent it by the shape number, the free band chain code, or the shape number. Okay, represented by the chain code itself. Okay. And with this is called the rubber trim technique. Okay, or the minimum perimeter polygon. You can see with this technique, okay, the error is at most square root 2d. D is the distance, the width of the grid. Okay, depending on the grid. Okay, but it can represent it by that. Next is called merging technique. Okay, the merging technique is like this. Suppose you got the red boundary, which is curvy. Okay, a lot of curves. Okay, you do the merging technique by you integrate, or basically you calculate. You draw a straight line. Okay, you draw a straight line along the boundary. You kind of like, it's more like the linear progressions. Okay, and then once you draw the line, there will be errors. Right? You accumulate the error. Okay, until the error reach a certain threshold. Okay, so you add the line, you add more error, until the error reaches a certain threshold, and then you stop. Okay, and you form a straight line along that boundary, and then you do and repeat it again. Okay, you start with another straight line. Okay, and calculate the error. The error got to be less than a certain threshold. Once it's about to reach that threshold, you stop. And then you change to another straight line. Okay. So it can be like this. And then change into the straight line, change into the straight line, and change into the straight line, and so on. Okay. And you end up with the boundary of the object. Okay? This is called the merging technique. Last but not the least is the splitting technique. Okay. The splitting technique is the technique to subdivide the boundary segment successively into two parts until a certain criteria is satisfied. For example, suppose we got a curve like this. Okay. Suppose we got a curve like this. We want to represent this curve by a straight line using the splitting technique. Okay, what shall we do? First of all, you draw a straight line. It can be represented by this straight line, right? Okay, that's connecting the starting point to the end point. However, this straight line, is it well representing this curve? Probably not. Now, we need to form a certain threshold. For example, here, the black line here is a certain threshold. We say that if the distance from the curve to the straight line is more than this threshold, you're gonna split the curve, the straight line. You're gonna have to split the curve into half. Okay. For example, here you can see the threshold, the maximum distance from the curve, the pink curve, to the green straight line is this much. And you compare this length by this threshold, you can see that this error is more than a certain threshold. When it's more than a certain threshold, you split it in half. Okay. So we'll split at that point where the maximum distance is. Okay. So you split this curve in half because apparently this straight line cannot represent this curve. Okay. So once you split in half, then now you got two curve segments. Right? You repeat the whole process. Okay. You repeat the whole process. For example, here, this curve segment, you draw a straight line. And then you measure the distance, the error. What is the maximum error here? The maximum error is here. Suppose this maximum error, is it shorter or longer than this threshold? If it's shorter than this threshold, you stop. Okay? So you end up with that one. Well, actually, yeah, you end up with this one. Okay? So actually, you're supposed to draw this one. Okay? However, this curve segment represented by this straight line. And you can see that the maximum error between the curve and the straight line is more than the threshold. Once it's more than the threshold, you repeat, right? That means you got to split this curve into two parts, which is this curve, okay? This is the splitting point. And then for this segment, you need to measure it again. So you measure this, and the error is smaller than the threshold. You don't need to split anymore. Okay, stop right there. And this one, okay, the threshold, the error is smaller than the threshold. Let's stop. And that's it. So this curve is split into 3 segments. Okay, and then you draw a straight line representing each segment. Okay, this is called the splitting technique. This splitting technique is much easier than the merging technique. Okay. Alright, for example, suppose you got a closed contour. The question is where to start. Okay, where to start if you got a closed contour. Usually the starting point are the 2 furthest point on the boundary. Okay. To furthest point on the boundary. So, and suppose we set this at preset threshold. So we start with this longest point away from each other. Okay, and you can see it's split into 2 segments. This one and the one above. Okay, the one above, of course, the error is more than the threshold. You need to split. So you mark a point of splitting right there. Okay. And then you erase that. And then you measure another segment, the lower segment. The lower segment is this much. Compare this error to the threshold. Is it longer or shorter than the threshold? Shorter. Is it shorter? I think it's longer. Okay, that's why I split. Okay, it's a little bit longer than the threshold. You split. Okay, so you split the upper one split into 2 segments. The lower one also split into 2 segments. Now you test each segment again. Okay, so this segment, what's the error? This much. Is it longer than the threshold? No, no more. So you don't need to split. Okay, you draw this straight line. Is this error, is this segment, the error is shorter than the threshold? No need to split. Next is this segment, error smaller than the threshold. No need to split. Last one here, this segment, is the error more longer than the threshold? Longer than the threshold, you split again. Okay, so you mark the point of splitting here. And then you do this one. Okay, this line segment, error so small, and this line segment, error smaller than the threshold. So this curvy shape is changed into polygon. Okay, it's changed into polygon. And that's it. It's that simple.
Can we split as much as we want?
Split.
Is the points. Is there any downside or splitting too much on the pictures?
What do you mean?
Let's say we got a line that is shorter than threshold.
Right.
We stay. Let's say I want to split more.
Oh, you want to split more. That means you decrease the threshold. Right? If you decrease the threshold, you could get more polygon with more size. Right? For example, here, if you got decrease the threshold, you can split it here again, but then threshold will be smaller and smaller. Okay, you get a more complicated polygon, that's all. Okay, so it depends on how complicated you want the polygon to be. Okay, so if you got the threshold should not be too small, okay, and should not be too large. Okay, the question is which one is just right? We don't know. Okay, nobody knows. Okay. Next is signature. Okay, once suppose you got the curve. Okay, you can represent this curve or this closed contour by signature. What is a signature? Signature means the radius is a function, is a 1D function. Okay, one-dimensional function along the radius. Okay, along the radius. What is the radius? If it's a symmetric shape like this, okay, the center, okay, usually we use the center of mass, okay, as the center. And then you go along the radius. So in this case, it's usually the angle would be from 0 to 2 pi, okay. So the horizontal axis always start from 0 to 2 pi. And what's the radius along the angle theta? Here, if it's a circle, the radius is always r, right? It's always r. In this case, this is the radius is a, okay? So you got a straight line. This straight line represents the boundary of the circle. Okay, so you change from 2D in 2D shape into 1D shape. Okay, into 1D, one directional shape. Okay, one dimension shapes. Okay, go ahead and draw this one. The signature for this square shape. I'll let you try that first. What do you think it will look like? Okay, you can see here that it starts at A, right? The distance from the center to the boundary is A. And then it's getting longer, 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 and the maximum is A square root 2. Okay. And how is it going? It's going to go like this. Okay. Go like this. Go to A square root 2, and then shorter down to A again. Shorter down to A again. And then goes up, same pattern. Okay, go down to A at pi. Goes up to A square root 2 at 5 pi over 4. And goes down to A at 3 pi over 2. Okay. Go up to square root 2A at 7 pi over 4 and come down to A. So these one-dimensional signal represent the square. Okay? Is it that easy? Normalize signature. You can normalize the signature by to be able to do the shape rotations, right? Rotation normalization means you select the same starting point to generate the signature regardless of the shape orientation. Okay. So we choose usually we will choose the starting point that's furthest to the centroid as the starting point. So if you got any shape and is rotated, if you start with the same starting point, which is the longest from the centroid to the longest distance, that's the starting point. Then every single shape, even though it's rotated, it's end up with the same signature. Okay, that's called the rotation normalization. The scale normalization means you scale everything to 1. Okay, you scale the distance from 0 to 1. Okay, so in this case, if the circle of radius A, if you got another shape, a circle of radius B, it's going to be a straight line, but it's going to be at different level, right? That tells us the radius. If you want to be scale invariant, you divide A by the maximum distance, which is A, and you end up with 1. You divide B by the maximum distance, which is B, and end up with 1. So in that case, so if you normalize the values along the arc to be from 0 to 1, you end up with the same shape, even though they are different radius, okay, different size. So it's the scale normalization. We could use other shape density function. Okay, you could use other shape density function. This is just one example. For example, you could have the signature, the histogram of the signature. Well, anyway, this is wrong somehow. Okay. Anyway, the boundary segment. Okay. A lot of times you set the segment according to the convex deficiency. Last time we learned the convex deficiency, right? Convex deficiency means you have the objects, then you draw the convex hull of the object. Okay. When you draw the convex hull of the object, this is the convex deficiencies. And then you can separate the objects into segments. Okay, depending on where it touches the boundary. Okay, for example here, this point is when it starts to change from convex to concave. So you mark this point. This is where it starts to change from concave to convex. You mark that point. Okay, so each marker is when it starts to change from convex to concave or concave to convex. Okay. Skeletons. Skeleton is another way to represent the structure of the shape. Okay. The way to do skeleton, last time we already did that, right? The morphological image processing, you can have the program to do the skeletons. Okay, when you got the shape, okay, you can erode it until it becomes skeleton. Okay. Usually, the skeleton is done iteratively by deleting the edge point. Okay, subject a certain constraint. Okay, and usually it does not remove the endpoints. Okay, it do not break any connectedness. And it does not cause extensive erosion. Okay. In 1967, Blum proposed a skeletonized process called the medial axis transformation. Okay. The medial axis transformation is like this. You start with a point P in the region R, and then you find the closest neighbor in the boundary. Okay. Find its closest neighbor in the boundary B. And if P has more than one neighbor, then it will belong to the medial axis, okay, of the regions. What does this mean? Okay. If P has more than one such neighbor, it is to belong to the medial axis of the regions R. Well, this is the way we do, okay? It's more like this. The way we do is that we think of the image as the Perry uniform, dry grass. Okay, it's like this. You got a shape like this. How you determine the skeletons? Last time we learned that to be the skeleton is like this. You fit the circle, right? You fit the biggest circle, and then the circle will be smaller and smaller and smaller and smaller. Okay. And then you track the center of the circle. Okay, that's the method for the skeletons. But this one, they say they think of the battery, and then you put the fire on the battery. Okay, you put the fire on the battery, and then it's kind of erodes. Okay, the battery is getting smaller. Okay, at the same constant speed. And whenever the two line, okay, connecting, okay, you're gonna get the skeletons, okay. So this is like this, okay. So this is the skeletons of this object. Okay. You get from this line coming in, and then it becomes like this. And this is the object shape of the skeletons of this object. We find that the skeleton quite unique, okay, for different objects, okay, for different objects. This is the way to represent the skeletons, okay. So instead of keeping the whole image, okay, we can just keep the skeletons, okay, of the image, of the object. Next is boundary descriptor. Once we got the boundary representation, now you can find some numbers to represent the boundary. Okay. Well, the easiest way to do is the length, okay. It could be the diameter, the intensity, eccentricity, the curvature, the shape number, we already told you that, right? The shape number. And then the last one is the Fourier descriptor. Let's take a look. Suppose we got the boundary, okay? The simplest descriptor for the boundary is its length. Okay, the number of pixels along the boundary that provides the approximation of the length. For example, suppose you got the chain code 0033002. Remember, the chain code tells us the direction that's going down, right? So, how do you measure the boundary of the chain code? Note here that from 0 to 3, it's actually, this is a 4-directional chain code. So, every time it's changing the direction, it's 1 unit, right? It's 1 unit. So, you're counting how many of them are there, right? So, you from 0 to 0, 1 unit, 0 to 3, 1 unit, 3 to 3, 1 unit, 3 to 3, 1 unit, and so on. How many numbers are there? How many units are there? 4, 8, 12, 16, 20, 22. Okay. So, the boundary is 22 pixels, or 22 units. How about the 8-directional chain code? 8-directional chain code, the boundary will be slightly different. If it goes left, right, up, left, right, up, down. So if it's a 2, 0, at 0, 2, 4, 6, the direction it's moving is 1 unit. However, if it's go diagonally, okay, like 1, 3, 5, 7, it is square root 2 unit. So you just count the number of zeros, 2, 4, 6. How many 0, 2, 4, 6 are there? 1, 2, 3, 4, 5, 6, 7, 8. So 8 units going upwards, right? 0, 6, 6, 6, 6, 3, 3, 2, 1. 8 units. Okay. And 7, 5, 5, 3, 3, 1, 1 is square root 2 units. Okay. So the distance would be 8 plus 7 square root 2. Okay, that's the boundary of the object. Okay. So you can represent the objects. The descriptor, one of the descriptor for the boundary length is the way you count the chain code. Okay, the length of the chain code. Next is the diameter. The diameter of this is representing the boundary, how big the object is. Right? Can represented by the diameter. Diameter means the maximum distance between 2 points on the boundary. So you just measure between 2 points on the boundary, and that's the length of the diameter of the object. Okay, that could be another description. Eccentricity. This is how measure how difference. So you're gonna have two things. You get the ratio between the major axis to the minor axis. Okay. The major axis is the length to the two extreme point, the line connecting to extreme point on the boundary. And the minor axis is the line that is perpendicular to the major axis. And it reached the maximum point, the maximum distance as well. So according to this is the major axis, okay, or the diameter, and this is the minor axis, okay. So according to this, you can draw the rectangle around the object. Okay. Curvature. Curvature, kappa, is the rate of change of the slope of the boundary. Okay. So if you got the boundary, the rate of change of the slope itself is the first derivative. Right? So if you want the rate of change of the slope, it's basically the second derivative along the boundary. Okay? Curvature along the boundary tells us whether or not it's going in, which is called convex, or is it coming up, out of the boundary, is called concave. Right? So the curvature is the thing that can measure the convex shapes, how convex the shape is. Okay. So basically, we represent it by it could be represented by the merging technique or the splitting technique, right? We just learned the merging or the splitting technique. So we represent the boundary by a polygon. And at each point of changing slope, that's the curvature, okay? So over here, suppose we assume clockwise boundary, okay? So this is where the curvature is less than 0. When it's a straight line, there is no curvature, right? Okay. And at this point is another curvature, K is more than 0. It's concave. Okay, convex means the shapes go inside the object, right? The boundary goes inside the object. Okay, concave means the protruding point. Okay, the boundary goes outside. Okay, and that's how you measure the curvatures. It's like you calculating how many curve, how many convex in the boundary, or how many concave points are in the boundary. Shape number, we already explained that. Okay, shape number is just the first difference of the chain code with the smallest magnitude. Okay, with the smallest magnitude. For example, here the Freeman chain code, okay, would be 0. Go to the right. Go to the right is 0. Go down is a 3. Go to the left is 2. Comes down is a 1. So you got 0, 3, 2, 1. You find the first difference from 0 to 3 is 3, from 3 to 2 is 3, from 2 to 1 is 3. And from 1 to 0 is 3. Okay, so this is the first difference, and then you start with the smallest magnitude, which is 33. So this rectangle shape is represented by the shape number 3333. How about this one? Go ahead and fill in. Find the shape number of this object. Okay, what you get for this one is 0, 0, 3, 2, 2, 1. The first difference is 0 from 0 to 0, from 0 to 0 is 0, right? 0 to 3 is 3, 3 to 2 is 3, 2 to 0, 2 to 2 is 0, and 2 to 1 is 3, and 1 to 0 is 3. Okay. And then you pick the smallest, the smallest magnitude, which is 0, 3, 3, 0, 3, 3. Okay. How about this one? 0, 0, 3, 3, 2, 2, 1, 1. Okay. And this is the first difference, and that's the shape number. Okay, next is this shape number, and that's, you can see different shape end up with different shape number. Okay. Alright, next, like I said, we can do grid normalization. Okay, if you got a curve and we do grid normalization, and then we start with the chain code, we already explained that. Okay. Last but not the least is the Fourier descriptor. Okay, Fourier descriptor you change the boundary position x, y, okay, into the Fourier domain. So we set S as sk is equal to xk plus j yk. Okay. And then we take the Fourier transform of this sk. Okay. When you take the Fourier transform of this sk, so this is the discrete time Fourier transform. You summing sk times e to the negative j 2 pi uk divided by capital K, k from 0 to capital K minus 1. Capital K is the number of points on the boundary. You end up with AU, okay, which is usually complex. And this AU, for example here, okay, you got the pixels, okay, these are the boundaries, you put in S equal to X plus JK, and then K from 0 to K minus 1, you sum up according to this equation, you got AU, which is the Fourier descriptor, okay. What's good about Fourier descriptor? You can go back, if you know the Fourier descriptor, you can go back and get the boundary SK by taking the inverse Fourier transform. Okay. When you're taking the inverse Fourier transform on every single point, okay, from 0 to k minus 1, you end up with the same original shape back. Okay. But the information is the same, okay, so you can have the information in terms of SK, okay, or in terms of the Fourier domain AU. However, when we construct the values with the first largest P point, instead of using all the K points, we sum with, instead of K, sum from 0 to K minus 1, we sum for just K point. No, this is sum for all K, I'm sorry. If you sum for P point, which is smaller than K, okay, you end up with only P. What happened to SK hat? What you guess? Remember, the Fourier represent the frequency, right? It's represented by the frequency. So at the higher values, that higher Fourier descriptor is the high frequency. If you sum from 0 to P minus 1 into the first P point, then you are getting rid of the high frequency. What happens when you ignore the high frequency? The object can be smooth, right? But this one, since we use the Fourier, since we use the boundary as the point, okay, so this is what we get. You can see this is the original boundary. You get the whole thing back, and this one we use 50% of the point. Okay, suppose this one you got 100 points, you only use 50 points on the boundary. You can see the shape doesn't change much, right? It gets rid of the low frequencies, okay? So if you use Fourier descriptor, it's a lot less information, okay? Half of it does not contain the details, right? You can still get the overall. And this one is 10%, you can see. 10% of the Fourier descriptor is still looks almost like the original. Okay? Use only 10% coefficients. Okay? However, yes, you can reduce to 2.5%, 1.5%, 6.63%, and the last one is here, this is 0.28%. You can see with the Fourier descriptor, it doesn't change the boundary much. So you can just use just the first few coefficients. Okay. However, the last one, the shape changed tremendously. That means you get rid of too much noise. Okay. This is probably no good, but you can have up to this. Okay. 0.6%. Okay. For the Fourier descriptor. How do you know which one is the 0.6%? That means you sum the coefficients, right? AU. Okay, the magnitude AU. Okay. The higher the magnitude of AU, okay, it represents the original mode. So this is another way to do, okay? Suppose we construct with the rectangle, the square like this with 64 points. If we use all the 62 points, well actually if you use just 2 points, it becomes a circle. So this corner disappears, right? If you got more and more and more and more, you start to see the corner, okay? And if you got 62 points, it's almost the same as the original. And here are some of the property of the Fourier descriptor. You probably have learned it in signal and processing. Okay, the Fourier transform. Okay, rotation. If you want to rotate the object, you just multiply by e to the j theta. Okay, in the Fourier descriptor, also multiply by e to the j theta. So many translation point. Okay, you can end up with the same Fourier descriptor. You could have boundary statistical moment to be descriptor. For the boundary statistical moments is similar to the signature, okay? But this one you measure the distance and then you calculate the mean. So you represent it by the one-dimensional graph, right? And then you find the mean, and this one is considered as the histogram. Okay, so to find the mean, you just have this formula: I minus m. M is the middle, the center in the middle, right? Square times GRI. And then you can find the second moment, third moment, and so on. Okay. So to implement the moment descriptor, it's basically very, very simple. Okay, just use the statistics. Second moment means you spread the curve a lot about the mean. Third moment means the symmetry with the reference to the mean. And so on. So you can have up to n this moment descriptors. Okay. Next is the regional descriptor. The regional descriptor could be intensity, area, compactness, and texture. Intensity is the easiest. You can have max, min, median values of the intensities. Area, you just count the number of pixels within the up regions. Compactness, however, is equal to the perimeter square divided by an area. This is also useful. For example, what's the compactness of this circle? What's the area, the perimeter of the circle? 2 pi r, right? The whole thing square. So you got 2 pi r the whole thing square divided by the area, which is pi r square. So the compactness for this circle is 4 pi. How about the compactness of the circle? This small circle is also 4 pi. How about the compactness of this rectangle of width 2 and height 1? The parameter would be 6, right? 3 times 2 is 6, and then square is 36 divided by area, which is 2 times 1. So 36 divided by 2 is 18. For the compactness of this rectangle, which is twice as much, you can see that it's also 18. Okay. You can see that the compactness is invariant to scaling, uniform scaling. Last is the topology descriptor. Topology descriptor is just counting the one that most often used is the Euler number. Okay, Euler number means the number of connected components subtracted by the number of holes. Okay. So this one doesn't depend on the shape, okay, but depends on the shape can change, okay, as long as it has how many holes, it can have the same Euler number. C is the number of connected components, H is the number of holes. For example, this picture, what's the Euler number of letter A? How many connected components are there? 1. What's the number of holes? 1. So the Euler number is 0. How about the Euler number for B? 1 minus 2 is negative 1. However, the Euler number, if it's represented by polygon, okay, if the region is related by polygon, we'll use this number instead. V minus Q plus F equal to the Euler number. V is the number of vertices, Q is the number of edges, and F is the number of faces. So it's 3. Last is the texture. Texture is used a lot to describe the regional objects, okay, the regions of the objects. Basically, texture can be complicated, okay? To measure the smoothness or the curviness or the regularity of the surface, okay? There are 3 different approaches: the statistical approach, the structural approach, and the spectral approach. We're going to talk about just the statistical approach, which is this one. You can find the edge moment of the gray levels. This is different from the boundary descriptor, except because this Ci is the value of the intensity, okay, not the distance. So Ci minus the mean, the whole thing to the n, times P sat. And then you can measure maybe up to 1, 2, 3, 4, 5 moments, okay? The first moment is represented by the mean, or the first moment represent the what? The average gray values, right? The second moment represent the variance, okay? Is the variance is represent the contrast of the objects. Okay? So it's a descriptor for relative smoothness. Third moment measure the skewness of the histogram. And 5 or more, there will be some meaning, but we don't know what they are, okay? But we know we can use it, okay? So when you got a bunch of data, this one statistical approach is most popularly used. Okay. Fourth moment represent the relative flatness of the histogram. Third moment represent the skewness of the histogram. And then you can use those statistics to measure things like the relative smoothness depending on the variance, okay? So it's the opposite of the variance, right? If the variance is high, relative smoothness is supposed to be low. And the uniformity of the texture. You could have uniformity of the texture using the P. What is P? P is the histogram, right? Here. Normalized histogram. PC is the normalized histogram. Okay. So this is the histogram square. Normalized histogram square. The contrast, we use this PZ times log base 2 of PZ. This is like the entropy. Okay, the entropy of the data. Okay, PC times log base 2 of PC. So, for example, here, if you got objects like this, you can measure here, this is the objects, here, objects, this objects. You'll see, you calculate all these, okay? First moment, second moment, third moment, uniformity and entropy, okay? Note here that the first surface is smooth, right? When it's smooth, the mean will tell us how dark it is or how bright it is, right? And the standard deviation would be small compared to the middle, okay? The middle here is curves, okay? It's not smooth. The variance you can see is very high, okay? And the last one is the circuit board pattern, okay? It has a certain pattern, okay? So the variance, not so much, okay? This is the relative smoothness. R is the relative smoothness. It says that the first picture is really smooth because it's 0.02. This one is very large, which is 0.079. And this is for the regular, is 0.17. Then you can use all others. Structural approach is a little bit complicated. You need the programming to do, okay? So you got to form the basic structure and then you connect them using these rules, okay? S equal to A and then A equal to BS and then repeat, okay? And to form the structure, primitive, you have to start with the primitive structure and then you connect them, okay? Put them together. Three features for the Fourier spectrum can be used for the texture. Okay, you can use three features for the Fourier spectrum to be used for the texture. So it could tell us the prominent peaks, the location of the peaks, and it can get rid of, you can get rid of the periodic components of the filters. This is the functions for the polar form spectrum, okay, polar form coordinates. Okay. And this is the objects, okay, this is the Fourier spectrum, and then you draw, this is the magnitude, and that's the phase. The angle of the phase. You can use it to measure the structure as well. All right, and that's it. Wow. Today is so short, huh? Only an hour and a half. Yep. So we are free. We are done for the course. Okay. Getting so tired. Okay. You got 2 weeks. Not free. Okay. You have 2 weeks to work on your project. Right? 2 or 3.
มัน
When
มัน4 3
3 weeks เลยเหรอ ยาว
แต่ว่ามัน